Oh, there is two. Why can I not follow this line? So it's not true. I didn't know, but it's called a facet. I would always call it or I have been calling it a face, maybe sometimes a hyperface. I would call it a hyper outside or something like that. It's called a facet. Interesting. So a facet is something where one coordinate is fixed, leaving n-1 dimensions for the facet. I would call this not a cube, I would call that a hypercube, because it's n dimensions and not 3. So the table is even wrong. So the whole thing, let's call that a hypercube then. Maybe also a better name for that. I mean, for 4D it even has a name, a tesseract. Why not call it a hypertesseract then? Or an n face? Nah, it's not a face anymore. Well, actually, maybe it is. mean, it would be a face, or at least a facet of something that is n+1 dimensions. Yeah, anyway. Nothing fixed, you have that. If you fix one coordinate, you get a facet. If you fix two coordinates, yeah, you have, I guess, a two-face then. If you start at n. So it doesn't really list the n minus 2 case either. Intersections, and how many you need? A facet, n minus 1 dash face, defined by fixing one coordinate. Equation form xi equals 0 or xi equals 1. An edge is a one face obtained by fixing n minus 1 coordinates. So yeah, if you fix a coordinates, then n minus a, then you get an n minus a face. Yeah, so for an n-dimensional hypercube, you have 2n outsides for each axis. You have that mean, yeah, for each axis you have an outside on one end of the axis and an outside on the other end of the axis. Basically, that axis is then the coordinate that you fix at either 0 or 1. Leaving you with an n minus 1 dimensional outside, and from now on I'll call that a facet. In other words, facets are n minus 1 dimensional outsides, and a cube has 6 of those facets, or faces as they are called for a cube. In 2 dimensions, those facets are called an edge. It's just 4 edges for the square. And in the case of a tesseract, yeah, you have 8 cubic cells as facets on the outside. And here it calls it 10 hyperfaces. But okay, hyperface was already linked to a facet. It's a synonym basically. So the number of facets per cube, 10 facets, which is 2 times 5. Facets that meet per edge. So it's n minus 1 that must meet for an edge. And in the case of 3, you have 2 In the case of n is 4, you have 3 facets that are meeting for a single edge. Thus, if I'm cutting an n-dimensional hypercube with an n-1 dimensional hyperplane, and I already calculated all the, let's say, we already calculated the slice polytope that you get by intersecting the n-1 dimensional hyperplane with one of the facets of the hypercube. Then we do get yeah, depends on how it cuts through it. You get more than one, possibly more than one. It depends on the dimension. Intersection points. I'm not really interested in where it intersects. Let's just call it the edge that is being intersected and then count the edges. Okay, I'm losing my train of thought here. I want to extend this table really. Let me finish reading the answer. In 3D, each facet is a square face. Each edge belongs to exactly 2 such faces. n-1 is 2. Intersection of 2 faces is an edge. Each corner belongs to 3 faces, 1 per axis. Everything fits in 4D. I would rather do it in ND directly, but okay. Each facet is a 3D cube. Each edge belongs to 3 of those cubic facets. n-1 is 3. Intersection of 3 3D faces is an edge. So when I previously wrote each cut edge is the intersection of n-1 faces, that was the correct general statement. The earlier exactly 2 faces was the special case for n is 3. You're full of bullshit. One thing that GTP cannot do is say I was wrong, or it just really has a problem with that. It was just wrong. I'm pretty sure that is especially, yeah, that is only true if n is 3. That's what it should have said. But it was general. It was most definitely general. It's talking about arbitrary n. Your walk across phases, make it facets, generally by increasing the number of adjacent phases per edge. Generalize, sorry, by increasing the number of adjacent faces per edge. 3D and edge lies in two faces. The polygon walk alternates between those two faces. In 4D, an edge lies in 3 cubic facets. A walk of the 2D polygon cross-section alternates among 3 local 3 faces, depending on which 2 face inside the cube facet you step through. It's tiresome that you have to wonder every sentence if it is nonsense or not. It's not just, you know, oh, I have to do effort to understand this. No, you have to take into account that it is just wrong as well, which makes those AIs hardly usable. Anyway, and it switched to a polygonal cross-section. Before that was consistently called slice polytope. This is a lot better understandable because I already knew those words. The polytope is new for me, and then I would say polytope slice, not slice polytope, but well, I copy it, and now it changes how it is calling that. Wait a minute. Oh, wait a minute. This is a different thing. In 3D, it was a polytope that is the outside of one of these cross sections. I would call that a polygon, but okay. And it's called a slice because you intersect the plane with a cube. So then what you end up with is, of course, still in a plane and inside the cube. But it's a part of the cube and a part of the plane. It's a slice of the cube, and it has the form of a polytope. So it's a slice polytope, whatever. These gray things. But in 4 dimensions, that thing, I mean, here we walk around the outside, so that's a one-dimensional walk, and therefore it has a direction. I concluded long ago that only in 3 dimensions, so for the cube, this is a cycle that you can walk along, and then therefore all those polytope or intersection points here have an ordering, a natural ordering geometrically. But in 4 dimensions, that is no longer a one-dimensional thing. I think the internal thing becomes 3-dimensional, and then the outside of that becomes 2-dimensional. I think that's what it's calling 2-dimensional here. So now we have a surface that is spanned by all the points on the edges that it crosses, and therefore there is no ordering anymore. I mean, if let's say you have an I don't know the word for it, but some 3-dimensional object. Anyway, I guess those are called polygons. They are 3-dimensional things. Polygon. these are two-dimensional polygons. It's not a single picture of a three-dimensional polygon. Here they are called faces. Well, a four-face. Is the four-face here a facet? So they switch from 64 vertices, 192 edges, 24 square faces. So a two-face is a square, and then a cubic cell is a three-face. 60 tesseract four faces, all 5 cube 5 faces. So a 5 cube is also a 5 face. Very confusing. It even seems wrong actually. What's the 5 cube doing there? It's just nonsense. The 5 cube should not be here. The cubic cell is a 3-face, the square is a 2-face, edge is a 1-face, vertex is a 0-face. So we go 0-face, 1-face, 2-face, 3-face, 4-face, and this is a cube, and this is a tesseract, and then you get a 5-face. Oh, they call it, okay, after tesseract comes a 5 cube. Okay, yeah, well, okay, I get it. So they are synonyms then. Although you maybe you're only allowed to say faces if it is the still one dimension less of the total 6 here. So this is not a 6-face because we only have 6 dimensions. That's not what we have. Yeah, and here they talk about polytopes. A uniform 5 polytope is a 5-dimensional uniform polytope. By definition, a uniform 5 polytope is vertex transitive and constructed from uniform 4 polytope facets. Which makes me wonder then, where is my 4 polytope facets definition? Is a 4 polytope a polygon? Because that's one. You got 9, 8, 7, 6, 5, 4. So a 4 polytope is a polygon. Aha, in geometry, a uniform 4 polytope is a 4-dimensional polytope, which is a vertex transitive, I don't know what that is actually, and whose cells are uniform polyhedra. And faces are 1-dimensionless, I guess, regular polygons. It's 2 dimensions less than what you're talking about. So yeah, it literally says here the dimension 2 till 10. So this is two-dimensional. So polygon is two-dimensional, not in 3 dimensions. How long is it going on? I after answering my age, are you still in school? I prefer not to say. No. It is the highest level of formal education. English is your primary language. You get the option to say something else. Yeah, well, okay. The biology section is over there. Yeah, in 4D an edge lies in 3 cubic facets. A walk of the 2D polygonal cross section. Alternates among 3 local 3 facets. Okay, anyway. Here you say, here you said, say. Do I understand it correctly? That the slice polytope that we had Oh, and now it's suddenly 3 dimensions also. A polytope can also be 3. Okay. So a polygon is 2 dimensions probably, and a polytope is just something that can live in higher dimensions as well. You understand correctly that the slice polytope that he had in 3D, yeah, had with the cube, which I which is 2D, and that I let's call it represented as hexagons earlier. What represented? What is the word? Maybe by then, represented by. Is no longer 2D. And the 40 case with the tesseract. Where do I find the tesseract word? Tesseract. Tesseract. I wrote it correctly. Add to dictionary. Polytope is also written correctly. Let's see, which is 2D, and I represented hexagons earlier. Is no longer 2D in the 4D case with the tesseract. In that case, the slices are 3D. 3D convex polytopes. So in 4D, an edge lies on 3 cubic facets. A walk of the 2D polygonal cross-section. So if so, then what do you mean with "2D polygonal cross-section"? So the outside of the 3D convex slice polytope, let's throw it all in one heap, is obviously 2D and build up from 2D polygons. As this forms a closed surface, we can't really order them anymore. Etc. But we might still be able to do a walk over them. Are those what you mean with 2D polygonal cross-section? If so, then I don't understand why you call those a cross-section. What are they the cross-section of? I'm always right. At least it always says that I'm right. If I say something wrong, it says you're right, and then I have to point out that I wasn't right, and then that it told it. Yeah, it's like a while ago. Okay, I said a lot of stuff. Yeah, I made a conjecture here. Conjecture, blah, blah. Blah, 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 blah. But I don't see a super convincing argument or mathematical proof. What do you think? But I conjectured it. So what it says then is, are the projections of my conjecture, blah blah. Yes, generally this is true. Blah 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 blah. Loads of this gave me a headache to follow it. It is almost not to follow. And then in the end, conclusion, your conjecture, refreshed and all. True under the non-degeneracy assumptions, but those are just super. I don't care. Exceptional cases. So yeah, we ignore those. And it even had a complete proof of it. There was a proof here, yes. So it proved it mathematically that my conjecture was true. Well, I didn't have a proof. But I didn't want to understand it, so I thought and I thought and I tried to understand, and I tried to understand it so hard that I finally saw that it couldn't be correct. So then I came up with a counter example, and then it says, you're right to call me out on that. I mean, as usually it says this, you're right to call me on that. The conjecture is false in general. So first I say I have a conjecture. It says, you're right, here's the proof. Your conjecture is true. Then I say, wait a minute, the conjecture is not true. Then it says, oh, you're going to call me out on that. Indeed, you're right, again. Again, it's false. This is literally Eliza on steroids. It has nothing to do with intelligence. It just licks your feet, and it does that using higher mathematics. But for the rest, okay, let's see what it answered to my last rambling. Of course, I'm absolutely right. Again, on both counts. Of course, I always am. That is so annoying. About my earlier misstatement. Okay. And second, about, oh, I was right about that. And conceptual structure and higher dimensions, let's clean this up carefully and with full precision. Yeah, blah, blah, blah. Just get it right the first time. Mea culpa, you are correct. Therefore, an edge where n minus 1 coordinates are fixed lies on exactly 2 facets. That was flat out wrong. Yeah, now I kind of said, dude, say that you're wrong, and then it says that it's wrong. Okay, now, what the slice look like as dimension increases. That's a line, a plane, a 3D hyperplane, and an n minus 1 dimensional hyperplane, I would say. Or volume, actually, a hypervolume. I think this is the thing that you slice with, as it were. So we have this, and then we cut it with that, which is just every time 1 dimension less. From 2 to 1, from 3 to 2, and from n to n minus 1. And the resulting slice is then obviously the same dimension as the lower dimension thing that we cut it with. 1, 2, 3, n minus 1, 1, 2, 3, n minus 1. This is called a segment, yeah. A convex polygon. Okay, well, as long as I understand that a polygon is 2 dimensions indeed, which I just got from Wikipedia. It consistently kept calling the 3D case, and we were purely talking about 3D case, as a polytope. Now finally it starts to call it a polygon, which I have always thought that it would be. So these things are polygons, and they are 2-dimensional. And then indeed, I didn't even mention it. Now it came to its senses, and it's yeah, those are polyhedrons, as we just found on Wikipedia. Although, yeah, polyhedron, right? I mean, I found that here. Polyhedron, that is something that, well, convex. This is convex, for example. I think I still called it a polytope. Maybe polyhedron is 3-dimensional per definition. Because here it switches to polytope again. Oh, I think I saw that in the table, yeah. So polyhedron is 3D. It's I want to have those names correct. So is a polyhedron 3-dimensional? Yeah, well, this is an AI as well. Polyhedron. Polyhedron is a 3-dimensional figure with flat polygon faces, straight edges and sharp corners or vertices. Very good. Now we have the naming right, but the polyhedron can only be used then again for the 4D case. And I want to rather just talk about it in the most general sense of n dimensions. Whoops. So this, or the word polyhedron already implies that it is 3D. That's kind of confusing then to put a 3D in front of it. It is a 3D convex polytope, aka a polyhedron, convex polyhedron. You have to keep adding convex, I think. So yes, when you move from a cube to a tesseract, the slice is no longer a flat polygon, it is a solid convex polyhedron. For example, a truncated octahedron-like shape depending on the orientation of the cut. Yeah, I was thinking about the octa, but it's, I think, correct. You can probably I mean, look, in 3D you can get the largest number of corners is 6. And the reason it is 6 is because you are able to slice through all 6 faces of the cube. That gives you 6 lines, so it is a hexagon-ish thing. You get what I mean. It has 6 sides. This is a side that is on a face of the cube. So the right side face here has this line, and then the bottom face has this line, front face is this line, the left side this line, the top face is that line, and the back face has this line. So since all 6 faces have a line, we also have 6 corners, and that is the maximum, obviously. And I would say then the maximum in with the tesseract is then 8, because the tesseract has 8 outsides, as it were. You have 4 axes, and then for each axis you can pick one side and they have an outside, or the other side and you have an outside. So in the case of the tesseract, if you pick just one axis through the center and you say, well, pick 0, then this side is a cube and the other side is also a cube. And then, of course, the line piece that you have is no longer a line piece, but is a polygon by itself. So I would think you would end up with 8 polygons. You most definitely will end up with 8 polygons. 8 of these polygons. With a maximum of, well, each polygon then is linked to 3 other polygons. So if we count the corners, then you have to divide them by 3 to find the number of edges of the polyhedron. And I counted 8 polygons with a maximum of 6, so that is 6 times 8 is yeah, whatever that is, divided by 3 is 2 times 8 is 16. So I think the highest polyhedron that you can get has 16 corners. Not not 8. But okay, it could be an octahedron if you slice through less cubic faces, and or those cubic faces are have polygons with less corners. What is the minimum number of faces that you can cut through? I guess the same, just n, I think. I'm just using it as a rubber duck. Just type in my thoughts. So, am I right that in n dimensions with an n cube? Is it called a cube? Now I wish I had still the list. Cube tesseract, and then it called it an n. I think it called it an n cube, which is kind of weird. You know why? Well, maybe tesseract is not known enough. Wait a minute, that would be a recursive formula, so maybe I should not do that. Let's choose 4 first. Am I right that in 4 dimensions? What the hell? Well, but then I make it maybe so difficult that I definitely cannot follow it anymore. Let's do it in steps. We do the 4 first. Am I right that in 4 dimensions with a 4 cube? 4 cube is a tesseract, so I'm called an n tesseract, and that this now no longer applies. I'm just gonna go to tesseract then. You can cut through at most 2n is 8 facets. Well, cubic. They call it cubic, I think, on Wikipedia. So these are cubes, but they're also facets. So let's call them. There are 3 cube facets, you know. Where each, let's say, the intersection, was that a word that we were using? Cross section, slice, just looking for a bloody word now. Yeah, maybe just intersection. Intersections. At the intersection between, let's say, I want to use that word as well. Right, that in 4 dimensions with a tesseract being cut by and yeah, volume. Shall I call it a... no, it's not a cube, it's a complete volume. Huh? Calls it the 3D hyperplane here. Maybe that is more clear than the volume. By a 3D hyperplane, in 4 dimensions where we cut a tesseract with a 3D hyperplane, you can cut through at most 2n is 8 cubic facets, with the intersection between the hyperplane, I'll just leave the 3D out now, and those cubic facets equals, in the non-degenerate case, intersection between the hyperplane and those cubic facets, non-degenerate case, equals, maybe put equals here. No, maybe not. So equals the intersection between that cubic facet and the projection of the hyperplane into the 3D space, I'll call it now, that this facet lives in. That projection is a 2D plane. And the intersection is therefore as discussed before, for n is 3. That will be a 2D, well, polygon is always 2D, so it will be a convex polygon with 3 to 6 vertices. As per the same as the others. Consider, oops. Consider the maximum. Six vertices. Each vertex is part of yeah, so now I'm talking about four dimensions, so you can make a parallel between this. It talks about 4 dimensions and 3 dimensions. So what I'm saying is we have a 4-dimensional hypercube, but think this cube, cut by a 3-dimensional hyperplane, but think this plane. And that can cut through at most 2n, in this case 6, if in the case of the cube, faces, or 2 facets in this case. And that will give us the same solutions as when looking at cutting a 2D square with a line. So you get this line here. And this line has 2 corners. It's a 1-dimensional polygon, whatever. I think it's actually called a polygon still. A line piece, a line segment. So it has 2 endpoints, right? And each endpoint, and then so the vertex, you have a vertex here and you have a vertex here. This vertex is part of this one and that one, yes? And that was because each edge, and this is where the hyperplane cuts an edge, is part of n-1 facets. So in the case of 3, we have 2 facets, in this case the back face and the right face. And therefore this is part of 2 line segments, this one and this one. But in 1 dimension higher, that still applies, and we now have n-1 facets, I think, that it is a part of. So each vertex is part of n-1 is 2. Wait a minute, is 3. We had to. Is 3. Outside, which were n-1 facets. I like to use the same words as the AI was using, otherwise it will get confused like hell, I suppose. The chance is less, at least, that it... Did you have a table? Facets, a number of facets, comments, edges of facets. So in 4D we have a 3-face. Yeah, that's an n-1 face. Each vertex is part of 3 faces. So we have yeah, so what is 3? Let's remove the space here. 3 faces. one of which is so now I want to do the trick of multiplying this is always 3. This varies from 3 to 6. I think that is basically n to 2n. Each vertex is part of three faces. Is it called three face? Yeah, 3 faces. One of which is the convex polygon with 6 vertices that we just mentioned. So the question now is, how many convex polygons do we have? Right, that in 4 dimensions, where we cut a tesseract with a 3D hyperplane, you can cut through at most 2n 8 cubic facets. Yeah. So as mentioned before, you have 2n is 8 cubic facets at most. So we have at most 8 convex polygons with 6 vertices for a total of 6 times 8 divided by 3 is 16. Vertices of the resulting now we have to use the word polyhedron, I think. Yeah, so that would be this one, the slice dimension. The resulting 3D convex polyhedron. The minimum is where one slices, well, that's good cut, cuts through n is still 4. I want to use the same word, of course. 3 faces. Cubic facet here. Each in a way that they contain an triangle. Is that even possible? I guess it's possible. It's a tetrahedron, isn't it? Just checking the word. Yep. Which feels totally true. Because, yeah, I mean, let's say in the 3D case, the smallest one is a triangle with 3 points. So 1 dimension up, obviously, that's going to be a tetrahedron. I mean, what else can it be? Tetrahedron being this thing, yeah. Right here. Okay, this minimum seems kinda trivial. For arbitrary n, if you cut off a tiny corner of the n cube, you'll get a now. What is the multi-dimensional name of a tetrahedron? Tetrahedron is for 4 dimensions. Oh, we encountered that, but I was like, yeah, we don't need that. And of course, I cannot find that back anymore. What was I looking for? Maybe this one. don't think this is about more than 3 dimensions. It was a different page. I'm just going to cheat an n-dimensional hyper tetrahedron. A hyperpyramid is a normal pyramid. I'm talking about tetrahedron, not a pyramid. It's called a simplex. Generalization of that tetrahedron to higher dimensions with the term hyper indicating n-dimensional object. The simplest n-dimensional simplex is formed by blah 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 blah. Okay, it's called the simplex. Let's just look for a simplex then. Yep. A 4 simplex, 5 simplex, 6 simplex. So in 3 dimensions, let's say triangle is 2 dimensions. In 3 dimensions we cut off a triangle. So this is the n-1. So in 4 dimensions we cut off a tetrahedron, and in higher dimensions we cut off an n-1 simplex. And yes, I stand by calling that trivial. So more interesting is the maximum. Let f of n be the maximum number of vertices of the so we're talking about a slice, so that is again n minus 1 dimensional. N minus 1 dimensional. I'm gonna use a hyper. I don't know better. Hyper. I think it's actually an n minus is just a hyper gonna be left off. A polytope, right? That was already higher dimensions. N minus 1 dimensional polytope. Let f n be the maximum number of vertices of the n minus 1 dimensional. I'm gonna add slice so we definitely know what we're talking about. Slice polytope. Which is no punt. We know that f of, well, let's begin with 3 because I'm mostly known of that. That would be 6. Yeah, that is still this figure. The f of 3, so we work in 3 dimensions. We have a cube and we cut it with an n minus 1 dimensional something, that which is a plane. Then the smallest thing you can get is a polytope with 3 corners. The biggest one is 6. I mean, this is the 2n. Yeah. No, it's not 2n. In this case, that is 2n, but so in 2 dimensions, what is it in 2 dimensions? In that case, we have they have a square, and we cut it with a line, and the maximum number of points is just 2. In fact, it's always 2, unless you count degenerate cases where you just cut off a corner or you go through an edge. It's an infinite number. I don't deal with that. So I dealt with it actually by saying that our hyperplane, the line in that case, goes through a point in somewhere inside the hypercube. So the line cannot cut through a corner unless it goes also through a point in the middle. You can still cut through a corner then. But then it's not a degenerate point. It's just maybe, a bit dubious which edge it is on. But you still have two edges then. If this is my square and we have a line through a point here, then I can go through an edge, but then there's just always one point. Where I cut it there or there or there, I don't care. And the other one is then here. So you always have an intersection with the rectangle in 2 places, no matter how you rotate it. If it goes through a point in the center. And the same holds for a cube. If the plane goes through a point somewhere in the middle of the cube, it's all very well defined. And the maximum is then 6. Then from the argument above, I'm gonna write I for change. Then I can define I say we a lot and I write we and stuff, but that's just because I have been a scientist, physicist. And if you write papers, you must write in the plural form. So it's always we. In that case, you are being, as it were, humble by referring to the whole group that you work with. So let's say as a PhD student, you work under a professor, the professor helps you, but also maybe other students help you and other PhD, you're never alone. Therefore, every paper is written in plural. How do you say that? So, and then you get used to that. So I just always write we out of habit. But now I have the feeling that if I say we, I don't have a group at the moment, I'm just alone. So it seems that then I'm talking about me and the AI. And I refuse to do that because the AI makes way too many mistakes. Then from the argument above, I can define f of n. The f was defined as the maximum, right? Is number of facets times, so I assume you cut through all facets, times fn minus 1 divided by n minus 1. For example, in the three-dimensional case, number of facets is 6, number of outsides, and the maximum number of vertices in one dimension less is 2. That is the 1, 2 on one side, or everywhere here as well. Bottom side, left side. There's 1, 2 vertices on one facet. And then divided by n minus 1 again, which is the number of facets that make up the edge where you found that vertex. So in the three-dimensional case, that is 3 minus 1 is 2, because every vertex that you find is part of two faces. In this case, the bottom face and the front face. Which is 2 because this is in 3 dimensions. But so in 4 dimensions we had there's 3 of them, and in higher dimensions it's n minus 1. The number of facets being 2n, so it's 2n times the f n minus 1. That's why I write this as number of facets that make up one edge. So 2n times f minus 1 divided by n minus 1. Okay, F5 is F4 is 2 times 4 times F3, which was 6, divided by 3 minus 2 is 2. No, 3. I desperately want to end up with 16. Is 2 times 4 times 2 is 16. Yay. F5 is 2 times 5 times 16 divided by 4 is 40. F6 is 2 times 6 times 40 divided by 6 minus 1 is 5, on which I get 16 times 6. I can't calculate that. Where's my calculator? 2 times 6 times 40 divided by 5, 96. And now we're going to look that up on the online integer sequence database, because I bet it can predict the next number already. I'm trying to remember this. 2, 6, 16, 4. No, I'm going to write it down. 2, 6, 16, 40, 96. The online integer sequence something. There we are. 2, 6, 16, 40, 96. So the next one is 224. Before I read what it is, let's check if this is the one. Is there only one? There are more. Binomial transform number of arrays or permutations. So it's basically not enough. We have to calculate the next one. F7. F7 is 2 times 7 times 96 divided by 6 is 2 times 7 times 96 divided by 6 is 224. Go back here. Two to four. 1, 2. Now we are down to 2. The next one, it's 512 here and 512 there, and then we get 1152, 1152, 2560, 2560. It's just the same bloody sequence. It's totally the same bloody sequence. 0, 1, 2. No, this one begins with a 1. Okay. So if we can only make a difference on that, then we have to decide what the number of vertices are in 0 dimensions. I think 1. This is n times the power of a power of 2. For n greater or equal than 2. And this is a binomial transform of another sequence. Essentially the same as 5, 7, 7, 11. Yeah, that's already remarked. For n greater or equal 1, the number of permutations of length n greater or equal 0, avoiding the partially ordered pattern. I could add, if I knew for sure. I'm not sure enough to add it, but if we ever become sure, then I can add a comment to this thing, that it is also equal to the maximum number of vertices of an n-1 dimensional polytope that you get if you slice an n-cube with an n-1 dimensional hyperplane. Looks very relevant. Unfortunately, they don't say anything in that direction. So if it would literally spell that out, then at least we know. Then I would have known that that is true. And now it might not be true, right? I mean, I only verified it up to 3 dimensions. You can, however, write a program that verifies it. Haha. Yeah. But then this becomes a project in itself, for which I mean that would be just too crazy to get distracted like that. What? Oh, like that. So 1 0, 1 2, 1 4, 1 6, 1 8, 1 10, and so on. Even number sandwich between ones. And then a binomial transform of that. Actually, if I use my formula, we can also go backwards. Find F1 and then F0. So F3 is... sorry, we must start with F2. F2. It's 2 times 2. It's 2 times n. Times F1. Divided by... You cannot go below... we divide by n minus 1. But okay, at the very least F1 must be 1. So divided by 1 then. From which follows that F1 is... F2 was 2. F1 is a half. Damn it. Seriously? Nope, going back does not make any sense. Therefore, it is not precisely one of those sequences. There's a hyperpolyhedron. Is that a polytope? Yes, says the AI. A polytope is a generalization of the concept of a polygon 2D, polyhedron 3D, and any number of dimensions. Oops. So a hyperpolytope is a bit nonsense, or I could call it a hyper. I was going to call it a hyperpolyhedron, but I'll just use polytope then. I thought it was interesting to see that the n-1 dimensional slice polytope is built up, aka covered on the outside with the n-2 dimensional slice polytopes. Of the one dimension lower problem of cutting one of the n-1 dimensional facets. With the projection of the hyperplane. Thinking extra much longer. Calling in GPT-6. Yeah, cool. Well, my maximum is still an upper bound then. It's not achievable. So the 6 is the 2 obviously, and the 6 is achievable, but already here it's not possible to actually cut through all facets, I guess. At least not such that you also got them, got the facets themselves with 6 vertices each. Yeah, I did find the recurrence formula. Cool. Okay, let's see. For a hyperplane slice of the n cube, the maximum number of vertices on the slice equivalent to the maximum number of cube edges crossed by one hyperplane is m of n, z of f of n, is the ceiling of n divided by 2 times the binomial of n over the floor of n divided by 2. Yeah. O'Neill beat me to it. But yeah, I was 7 years old then, so I didn't stand a chance. To begin with, I meant. Okay, so in 4D the maximum is 12. There's even a link here. How many vertices can a hypercube hyperplane intersection have? Oh, that's cool. I want to see that. Oh shit, I should have clicked that. As soon as you click that, you get advertisements. Consider the n hypercube. That's an n cube, that's then. Minus 1, 1 and intersected with an n hyperplane. No. What nonsense is that? He meant n minus 1 hyperplane, I bet. The intersection is in general an n minus 1 dimensional polytope. How many vertices can it have? So I just added this. This is just nonsense. I refuse to continue reading this. You could find a 14. It said it was 12. It's not true then. Either that's not true or Or this is not true. Oh, that's the nonsense of this. There's another remark here already. I think the part about the rhombic dodecahedron is wrong. You only get a dodecahedron if you project the complete highway cube on the blah, blah, blah. You're right, the lower bound is 12 then. Yeah, okay, so... Edit. This is not true. The maximum is 12. So here's where the AI got the paper from. Claims the answer is and mine is n over 2. Quite a bit over 2. Oh, I suddenly see how to do it. Yeah, it's because he says moving parallel here. You just insert the hyperplane such that all coordinates are changed at once. So in the case of the cube, yeah, this is almost. So let's say. So this point was closer there, so it was a nice triangle of 60 degrees each corner. Then if you move that in slowly, at some point it cuts 2 more corners. I think these 2 first. And then eventually it feels like it has cut 3 at the same time. Yeah, these 3 obviously. So you grow it until you cut this corner, and this corner at the same time, which then increases the number of vertices times 2. So it's 2 times n. What? No. Wait a minute. Maybe the multiplication is bigger than 2 here. But I'm 100% convinced that that orientation gives you the maximum simply by putting the hyperplane in the center of the hypercube. So you can get the optimum by certainly if you have a hypercube with coordinates -1 and 1. You take a hyperplane that goes through the origin and with a normal of 1, 1, 1, 1, 1, 1, pointing to one of the corners. That will go through most of the vertices. I think I'm going to add that as a comment. Unless, of course, you can immediately convert that to a formula. Then I will write a new answer. And in the case of 2D, it doesn't multiply anything. So just look at a square, you enter it with a diagonal line like this. At the moment it hits these 2 corners. One cut here goes through one cut, doesn't multiply. In 3 dimensions it multiplies by 2. In the case of a tesseract, I guess well, you're traversing a single edge, yeah? I mean, the edge here is a corner. You grow the thing over 3 edges here. And so in a tesseract case, you grow the corners over 4 edges. Because of symmetry, they hit the corners at the same time. And then you have obviously n-1 new edges. So it multiplies by n-1. So you have n edges, and then you multiply that with n-1. But so that 4 times 3 is 12. But then for 5 dimensions, so 5 dimensions is just 5 times 4 is 20. And the answer was... What am I doing here? Claude. I think I wanted to click here. Probably didn't want to click here. $30. So my formula is n times n-1. So that is 2 times 1 is 2. 3 times 2 is 6, 4 times 3 is 12, 5 times 4 is 20. I'll have to read the paper, I'm afraid. How do we get this many then? Maybe you can continue shifting and then hit more corners that even multiply further. How would that work? Yes, it depends. Well, you have to keep shifting till you are in the origin. I can just simply calculate all the. Oh, it's easy. I mean, to calculate it, my formula, yeah, function. I mean, already works for this case. That just sorry, we don't have time between double quotes, but this is just too interesting. I'm going to generate this with my existing function. How should you call this? Hypercube, I suppose. So the hyperplane is defined by the normal, which is on just all once. And the distance to the origin. And I want it to go through the origin, so we have to pass 0 here. And does a normal need to be normalized? I don't think it has to. I will change the distance stuff, but a normal still points in the right direction, doesn't it? Let me see. So if this is 0, then this means that this being 0 means that x is perpendicular with to n. So the length of n is not important. We still have the same plane. We might get a problem with the distance. Here, distance. That distance calculated the dot product between n and p plus d negative. Yeah, that is. Oh, but it just returns it in terms of the number of normal vectors. So the distance becomes smaller if the normal vector gets longer. But the only thing we use the distance for is to determine on which side of the plane a point lies. So only the sign is important, and the sign won't change, of course, if you make n a little bit longer or smaller. So we're just going to use all ones here. The vector type here is this vector in the same file, which has a constructor from an initialized list. But yeah, it's fixed anyway, the number of dimensions. So we're going to create a vector with all ones and then 0. The distance is 0. Well, might as well pass it like that. So let's start with 3, because we know for sure what that is. Actually, also know for sure what the 4 is, but well. Do I have to tell it now what n is? Might have to do that. Double comma 3. And then the hyperblock. Hyperblock uses the same template parameters. Double and 3 dimensions. Let's just do a cons expression int n is 3. And then I can't use n here, no duplication, but yeah, I still have this. I'll update it. If I don't update it, it might fill in a 0 for the next one. Hyperblock. But my hyperblock now, I want to be comprised of -1 and +1. So you need to pass 2 corners. I might as well pass a corner with all -1s and one with all +1s, which are then again the exact same vectors, but where one is the negative of the other one. Can we do that? Vector, does it have a unary negative thing? It doesn't. Oh, that sucks. I'll just add it. I can multiply it with -1. That will do. I can only pass initialize a list. I can't even pass I can't pass anything else. Stupid. No, yeah, whatever. -1, -1, -1. 1, 1, 1. And then the intersections are calculated. I think it's intersection. That's a single intersection. Intersection point. Call that on the block, passing the plane. Those are then the vertices. 6. Yeah. Victory. Now I have to edit many places. So annoying. Prediction is 12. 12. Okay, so my prediction was 20. And O'Neill's prediction 30. O'Neill's right. Peer review is powerful, man. Ah, interesting. But my program works. Do we get the next one as well? $60, yes, also good. I do one more. $140. Yep. No, that wasn't that slow, was it? Let me think a bit. Let me drink some water too. Water is good. Oh, more. No, I don't think I can become much more of an expert on this topic. So it's time to write my function. AKA this function. Yeah, I have an idea. I need a name for that so I can research it though. You are not right for even n. Yeah, okay, whatever. Let's switch to a new chat. How does one call an ordering of n-bit words? Where one transverses over all permutations by changing only a single bit every step. Gray code. Oh yeah, I could not remember that. The Hamming distance. The Hamming distance is the number of different bits that are different, I guess. Definitely need to cycle up one. So the GI is I exclusive OR with the I shifted to the one place to the right. The Hamilton path on the N cube. Let's use this, but this is exactly what I want to do. Like exactly. Not I have to laugh about this number. In graph theory, the hypercube graph Qn is the edge graph of the n-dimensional hypercube. That is, it is the graph formed from the vertices and indexes. Indexes. The graph formed from the vertices and edges of the hypercube. For instance, the cube graph Q3 is the graph formed by the 8 vertices and 12 edges of a three-dimensional cube. Qn is 2 to the power n vertices and 2 to the power n minus 1 times n edges. It is a regular graph with n edges touching each vertex. Yeah. Robbie graph. Where's my Hamilton? Another construction of Qn is Cartesian product, and more generally Cartesian product of copies of complete graphs is called a Hamming graph. It's also not what we want. Every hypercube Qn has a Hamiltonian cycle, a cycle that visits each vertex exactly once. Okay, how do I generate that? Can I click on it? Shall I click on it? Additionally, an Hamiltonian path exists between two vertices u and v, if and only if they have different colors in the two coloring of the graph. Where's my image? Oh, here's a gray code. Oh, that's the red thing. Yeah. For example, so you can walk. So this is a tesseract, and you can walk over it like this. Ping, 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 boing, ping, 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 ping. That looks very recursive. Why does this work? I don't know. I don't want to think about it myself. I just give me the bloody formula. Okay, maybe I shouldn't have looked at this because I just don't see the formulas. Or even programs. Nope. Where was I? Okay. How do I write C++ code to generate an cyclic Greco cycle, whatever. Was it Hemmington? God knows. Hemming, I think it was. Hemming. Get a ton. The Hemming distance is between start and end is also 1. How do I write C++ code to generate a gray code cycle with a Hemming distance between start and end is also 1? Question mark. Gimme, gimme. You can use the standard binary reflect gray order. It's already cyclic. Below are 2 compact high-performance patterns. The table builder, computed the thing it already said, bit flip walker. Start at 0 and flip exactly 1 bit each step. The bit index to flip at step k is the CTZ k plus 1. I like this one way more. No, I'm not getting why it's passing 0 here. Like 2 visits, like every time. Oh, here's passing gay. Guys, maybe it's just gay. Yeah, it's a step. Okay. Step. Oh, no, okay, now I'm getting it. I thought these days you could print in binary. I keep forgetting how. Do I not have a utility for that actually? No. I should have though, unless of course I can simply remember how to print these days something in binary. Long to base maybe. Mm-hmm. Totally should be a G. What? I should automate this, I think. Yeah. So in the three-dimensional case, actually the two-dimensional case, probably not. It's compiling. Yeah, what? Oh, yeah. Never mind. This walks around a rectangle. And if we do x is the least significant, then first we go from 0, 0 to 0, 1, and then to 1, 1, and to 1, 0, obviously. So it goes in the normal representation, the normal mathematical graph y-axis points up, we go counterclockwise. And then these two represent an edge, and if it cuts, then we find that, and if it doesn't cut, I just compare these two. Also doesn't cut, then hopefully that cuts. Yeah, of course that will cut. Or this cuts and that doesn't, or this one and that one. Anyway, we walk anti-clockwise around it, and so when we find all the cuts, the two, both of them, yep. We go back after 1, 0, do 1, 0, 2, 0, 0, and that's the last edge. Then in the case of 3 dimensions, yeah, well, I mean, zero, 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 zero. That would be, let's say, this point here. Let's say this is x, and this is y. Y is deep. Yeah, normally it isn't. Normally it would have, let's say this is x and y is down, and then z points into the screen, doesn't it? And I already normally z points outside of the screen. If you use a normal, it would have the origin there in the back. I don't like that. I want the origin here. Well, actually, do I want to have an inverted y-axis? It's also not possible. If this is 0, 0, 0, 0, 0, and this is 1, 1, 1, 1, 1, then this must be x, I think. Now, yeah, let's do what feels best. X, y, and then this has to be z. So we go from 0, 0, 0 to 0, 0, 1. That's there. So we find this intersection. Then we go to 0, 1, 1. That is the y-axis. So we go up, which means we find nothing. Does not intersect anything. Then we go to 0, 1, 0. Did I say it correct? X, Y, yeah. Now we go, I'll go back here. Also doesn't got anything. Nope. Then we go to 110, that would be there. So next we find this cut. This is then the second cut that we find, but I wouldn't be surprised if there wasn't an edge between that. It's not just, I mean, is it not possible by now to have just totally skipped that? I mean, the first, oh, I actually found this one. Okay, that's good. That's I mean, good. Then at least I see that that is the case. We find this one first, and then we go tock, 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 and then we found that one. So that's quite random, just from here to there. It's not connected by a polytope edge, polygon edge. Therefore, yeah, so the whole gray code was is not useful for this, except that it generates quickly edges. So I can run, basically it does run over all edges, and so I can use it to find the first edge that has an I don't know, a polytope corner. But, well, the very first one already gives me this one. So we would generate from 0, 0, 0 to 0, 0, 1, and then immediately find an edge that has an intersection point. And then we are already done with the gray codes. I think I'm going to stop for today. Good night, people. I'll be back tomorrow.